we'll change to another topic. Chapter 7 is wave. Actually, it's basically plane wave, so-called plane wave. But we'll start with write down the solution first. And we also we start with a single frequency that makes things easier. Oh, the chart is small. So first you write down the Maxwell equation. Now for the wave, we will talk about wave propagation. We just ignore all the sources. We assume the wave are already excited somewhere, and then it's just propagating through a space or through a medium. So in this space, there's no other charges or current. So the right-hand side of the Maxwell equation are all zero. So your divergence B is zero. Obviously, divergence B is always zero. And then the two other Maxwell equations, the Faraday's law is still the same. So E is minus positive B positive T. And then curl H is now this is positive B positive T. Right. And that's fine. So get rid of all the sources or current density and charge density. And now this set of equation is very symmetric between electric field and magnetic field. So this basically the difference is the sign. In the curl equation is a negative sign, this is a positive sign. So that is the only difference. And obviously you need the relationship between D and E and D and H. Now for a single frequency, so everything depends on minus I. Later on, we'll actually going back to this partial paucity a little bit when we try to divide something. But when we divide the plane wave, we just assume this as for a single frequency omega. And now for that, you can just relate the D and E is D is epsilon. Epsilon is in general should be a function of omega, so some function of frequency, and it can be complex also. But for now we're treating it like a constant, and for the first case, we're treating it also like a real function or real quantity, and then H is B over mu or B is mu H. Okay, so now we can look for a solution. And actually, before we look for a solution, we can write down the solution for each of these this quantity. And since we'll try to write down the Helmholtz equation in 7.3. So first step is changing partial T to minus I omega, because everything depends on this factor. So take the time derivative, we pull out the factor minus I. So basically changing these two equations. So the Faraday's law becomes del E S I omega B, and curl H is minus I omega D. Okay, so that is straightforward. Now to divide the Helmholtz equation is a bit trivial. And by the way, once you do that, these two are all obviously satisfied because you take a divergence of that. Divergence of curl is zero, so divergence B is zero. Divergence of curl is zero, divergence B is zero. So these two are automatically satisfied. Up to this level. Okay, so we only have two equations to work with. Now to derive the Helmholtz equation, because of this symmetry obviously quite obvious, you can just take another curl, then the right hand side is curl B, which is mu times curl H. So curl H is given by that. So that will allow you to write a single equation that relates, and D related to it. So like let's write curl of curl E. And you can use this identity, curl E is, I think it's gradient of divergence of E minus Laplace E. That's just a vector identity. Divergence E is 0, right? That equals to R. Using this equation, the I omega curl of E, right? And now you use this one. Curl B is just mu times curl H. So I omega mu times curl H is minus I omega D is epsilon E. So altogether, you multiply I and I, minus 1 and minus 1 is positive. This is minus, we have mu epsilon, and we have omega squared. Okay, so the Laplacian E, not negative sign, equals to this one, or you can put it in the same equation. I think I get, hopefully I get the sign right. Changes, did I get a sign right? Did I? So maybe I minus I omega curl B. Or maybe I used the sign, this mechanism 2 times. Actually, I used curl. This is just this one, curl of B. So I should just copy I omega. And then B is mu times H. So this becomes curl H is minus I omega. D is epsilon E. So I use it double use the negative sign. So this is a piece. So altogether, Laplacian minus a plus mu epsilon omega square. This operator on E equals to 0. So this is a Helmholtz equation. I think when we derive the green function of the Maxwell equation for the full Maxwell equation, we did that before. So there's a k square here. We call it k square when we calculate green function for the wave equation. Okay, so and in this case, actually, we doing exactly the same. We'll call it k square. So k square is defined as mu epsilon omega square. So k will be square root of mu epsilon omega with a plus or minus sign. It can be plus or minus because this is defined the square quantity. So just k is can be positive or negative, and then the equation becomes a Helmholtz equation. And both E and B satisfy the same equation. E and B or E or H, that doesn't matter. Right? Now, you can solve this. Obviously, there's a Laplacian, which make it the solution is can be complicated, but the easiest one to do that is assuming what we call the plane wave, which means you can transform to a coordinate that this variable depends only on one spatial spatial coordinate. And later on, you can rotate it back to pointing at any direction, but initially you can change your coordinate system. Like it's only all depends on x. The Laplacian becomes p squared dx squared. So everything just depends on x. So then the equation becomes simple. P squared dx squared plus k squared of whatever that e and b. That equals to 0. And so you know how to solve this, right away. Yeah. So this so everything will be proportional to. Let's just write down the electric field. So we like there's two possibilities. One that e to the I kx, and then because this is second order equation, there's two solutions. Basically using this, there are two possibilities, right? And then so the solution of second order equation has two separate equations, and then a general amplitude on each of one. So that because it's the equation is linear, so you can multiply any magnitude. So that should still be fine. So this is after you do the Fourier transform. So in the just single frequency of E, and not including this exponential time dependence. But if you want, you can add that back. So E now becomes x and t. It's like E sub 1 the I k x minus omega t. That's e2 e to the I minus kx minus. Okay, so there are two possibilities. Okay, now when you write it this way, you can see the physics of this term. So this is an exponential function of I times a phase. So this is the phase of the exponential function. So the phase is let's call it phi. It's not the cylindrical azimuthal coordinate. Just the phase. It's like the first term is kx minus omega t, right? That's the phase. But then you can also write that like pull out the k factor, kx minus omega over k t. Okay. Now assuming k is positive, which is the positive sign of this one, so omega over k will be this omega over k in here will be just 1 over omega over k using the positive sign, because we already use the sign in here. This is the positive term, this is a negative term. Right. And you identify this, it's like how the phase will propagate in time. So x minus a something times t. Obviously, this factor will have the dimension of a velocity. So this is how the phase change in time. Or you can say that if you go with this velocity omega over k, then the phase will be constant. Right? You move with this direction. So x minus this phase velocity times t, then you basically the phase will or the phase is propagating in this speed, right? So this is called a phase velocity. Phase. Okay, and
is it C only when it's in vacuum?
Well, no, when in vacuum now, in vacuum, so this is mu epsilon for general medium. In vacuum, the V phase, this is for wave in vacuum, then obviously you just change mu to mu sub 0, epsilon to epsilon 0. And now we can identify that as C, because that is how we define C from the Maxwell equation. At first, we just assume this is just C is just to represent this quantity, this string quantity that we saw from the Maxwell equation. Maxwell equation, we have this mu sub 0, epsilon sub 0 going around if you go to the vacuum. And to write it in a nicer form, we actually use C to represent this quantity. But at that moment, we have not identified what C is. And now after you solve for this wave solution of wave, or solution of the wave equation, you see that this C for a plane wave is the speed of light. It's the speed of the phase, how the wave, the phase is propagating in time, the propagating speed of the phase, right? And this is also means that x is going forward in time with this speed. So the wave is propagated in the forward direction. So basically, if you want to keep the phase the same, x will be equals to omega over k over t, at omega t times t over k, or x equals to this root. If you stay with this point, x is propagating with v sub p times t, then the phase will be a constant, and that means that this is the speed of how the wave is propagated in the forward direction using the speed c. Okay, and for vacuum, this is the only wave speed we have. And later on, for a medium, when this mu and epsilon depends on frequency, then the wave, the phase velocity is given by that, but for a modulation of the wave, it's propagating in a different speed. So for a plane wave that is just single frequency, so the amplitude will be the same, you propagate in time or space or whatever. It's just a single sinusoidal wave. But if you have modulation, slow modulation of the frequency, then it propagates in a different speed. And later I will divide the form of this. This is also called the group velocity. Right. And that when you have dispersion means that these things depends on frequency. Right. And then you can define that. But for vacuum, there's no such thing. Vacuum is mu 0, epsilon 0, just constant, or for all frequency, then the Vg will be equal to P. The phase velocity and input velocity will be the same. Okay, and the other term of physics is just the same, except that now with this change to negative sign k, it means now this becomes a minus k, right? Then to have a constant phase, you need to propagate in negative velocity. So the wave is propagating in negative direction. Okay, so this is a general solution expressing the wave propagating. One is the positive x direction, the other is negative x direction. And likewise, you can write down the solution corresponding for B also, but we'll continue that later. So, because there's some relationship between E and B, obviously, because you have Maxwell equation, they are related. So there's something we can derive from the relation between E and B, and also the direction of the propagation. We are now assuming that is x direction, but we haven't actually specified this E1 and E2 yet. I mean, although the magnitude is arbitrary, later on we'll see that there's a constraint that because of the divergence equation. We haven't done that yet, but we'll do that later. So we have written the solution for the Helmholtz equation for at least just the electric field. And remind you the Helmholtz equation is this, that this is derived from the Maxwell equation, but with the single frequency omega. we are assuming that everything oscillates in single frequency. And both electric field and magnetic satisfy the same equations. E of B injection. So either E or B satisfy the same equation. These are in the oscillating with the same frequency of B. Right. And the solution last time we just say we are using one Cartesian coordinate and say found the plane wave solution. So E, yes, like if it depends only on X, then it will be like you have two solutions, the constant amplitude times the I. You have one solution at kx minus omega t. The other is E2 minus kx plus omega t. Right. And so the two things is we assume it's just simplify the notation. Say like this depends only on x, but we can always choose your coordinate. X, y, z, right? And it depends on x, but you can always rotate your coordinate system so that the dependency instead of x is on the line, any line. So instead of x, you rotate those in. So originally, this would be your x for this reason, but you rotate it. So this would be a general direction. You can call this a direction. Like if there's a unit vector instead of x hat, this is a unit vector of, and just use n, vector n, which is unfortunate because we have another n later. We commonly use what we call, we actually talk about that. There's index of reflection or reflection, reflection coefficient. Like, and so this is a vector n. That one is a scalar n. So don't get confused, right? So instead of this kx, this becomes this k dot n. Just basically change it. K dot n. Right. So that's a plane wave solution. I should say as k dot xn. K dot xn. X is not the x coordinate. It's just just like the the radial coordinate, or you can call it R. And this is like a radial unit vector n, but it's now using n. So this is changing the notation to 7.8. Actually, Jackson used it now. It doesn't like wave vector. I usually use wave vectors. Instead of this, let's see, k, keeping the k, but x dot n. Originally is x, right? This x dot n. Right. Originally this is a minus, and this should be a plus. Right. That becomes two solutions. So this n direction, and then the radial position vector dot into this direction, meaning the coordinate along this direction is just like what we used to have this x direction. Okay, so it's just a simple generalization instead of just using, or you might say just rotate your coordinate system such that x is along n, so you can get the previous expression. But now generally you don't need to do that and just write in vector form like that. What I was doing that is express it as a wave vector. This is a wave number k, but the wave vector is you can define it as a wave vector, wave number k times n. That would be a wave vector. Then this k x dot n is just k dot x, and many people are using this notation instead. It's a little cumbersome to write like k x dot n, but anyway, just to use that. But we'll just follow it, and later we might change it back. Okay, so all right, so that is the electric field, and obviously you can write down the solution for B also. And so far we are assuming this is arbitrary, but later we'll have a restriction on this amplitude. They are not exactly arbitrary, but we'll get it in a moment. And then likewise for the little field, we satisfy the same equation, so we have the similar solutions. But then it has this magnitude, B sub 1, B sub 2, but then they are actually related to the E sub 1, E sub 2, and we'll also get that in a moment. Okay, so that is trivial because it satisfies the same solution, so that therefore the formula should be the same. And now we go back to this. If you use this and you plug that back to the Helmholtz equation, the Laplacian obviously basically changing to minus a squared n dot n. Right? Because you have all these factors. This is you do the Laplacian. So basically you have n sub x times x. This factor is n sub x times x plus n sub y times y, n sub z times z. And this is partial x, partial square, partial x square, plus partial square, partial y square, plus partial square, partial z square. So operate on these x, y, z coordinate. We multiply by. We'll differentiate that 2 times. You have the minus k square, and then like this is nx squared plus ny squared plus nz squared. So get n. Okay, and then combine with this one, so you get pretty much the same as what we have. So basically, this 2 term has to be combined to this. I mean, combine the zeros, so k squared n dot n. It's omega squared. Okay, and just like what we had before. I mean, therefore, if n is real, obviously n dot n is 1. So we had what we had before. If n dot n is real, then we have the same. So k is plus or minus. So that is for real n dot n. For that's a case later on text we'll talk about complex n. It's a little bit strange to call it the univector complex, but the Jackson used that term. It's understand as the similar to this k vector has a complex. Instead of using a complex n, we might use a complex k, which is more easy to understand. Right? The direction usually you don't call it complex, but Jackson did anyway. So so that is we'll talk about that later actually. And so we will talk about the other case for now. So this relationship between k and omega, this is what we call the dispersion relation. And for the simplest case, is that mu and epsilons, if they are constant, and this dispersion relation we call it actually non-dispersive. It actually not if the phase velocity doesn't depend on omega, that's what we call non-dispersive wave. if this factor depends on omega itself, frequency or wave number, whatever you have, it's not a constant, then we call that the dispersive wave. So that later I will work on the group velocity for phase waves, for the dispersive wave. Okay, and now up so far is we get back to what we had. So the velocities of, I can say this is the first one. The phase velocity is still omega. Okay, that is the same. It is, but we are using a more general expression for this coordinate in the phase instead of x. We call it we have this x dot n. Okay, so the next step is find out the constraint between this e, this amplitude e1, e2, b1, b2, and one is that you go back to the either the Gauss law or the divergence B is zero, so both will give you the same similar the restriction. So first we use divergence E is zero. Actually, originally divergence E is low, or divergence D is low, but in vacuum with wave propagation, assuming no charge, then it's zero. Then we put that back to here. So we take the divergence using this dependency. Obviously, you can work on term by term. So it's because they don't have the same sign, right? If you work on one term, we pull out a I K N dot into the E for this term. This one will pull a minus I K because there's a minus sign here. But for either one of them, either you pull out I K times N or minus IK times N, you dot into back to the electric field that is zero, so that implies K dot N or Kn dot E is zero. Okay. So it means that the propagation direction is perpendicular to this electric field, or N dot E sub 1 and N dot E sub 2 is both a zero. These magnitude are not totally arbitrary. They have to be perpendicular to this propagation N. Okay. Can you follow that this argument? So this because I didn't work out the derivative. The derivative should be trivial. So you have this is just partial E sub x partial x. But whatever the partial derivative is operate only on the exponential factor. And this is n sub x times a, n sub y times y, and so on. When you take the partial derivative, say for the x derivative, you pull out I, k, n sub x, right? And then so on. The other, and then you add the 3 becomes ikn vector, and then you dot back to the electric field, right? And so the direction of electric field and magnetic, first electric field must be perpendicular. So electric field propagating. So E sub 1 or E sub 2, electric field must be perpendicular to the propagation direction. Okay, and likewise, divergence be zero. So the same thing applied to here. So n dot b sub 1, n dot b sub 2. The n dot b is also zero. But that trivial. Okay, so the last one is you go back to the equation 7.2. So you can use either one. either use the Faraday's law or Ampere's law, right? If you use the Faraday's law, your curl E plus or minus I B is 0. Okay, so that's just the Faraday's law. The Faraday's law curl E origin is minus partial B partial T, but partial B partial T pull out a minus I omega factor. That becomes plus I omega B, and then move to this side. That's the equation. Okay, so in this case, likewise, you need to pull out term by term. So you have two factors, right? So you have this factor or that factor, right? I mean, two terms. You have this term and that term. So this term is related to this term, and this term related to this term. So similarly, the curl is when you operate on this kind of exponential dependency. So that we pull IK, but then IKN, but it calls into E. So K for the two terms, it can be plus or minus N cos the electric field. So E either plus or minus for these two terms, or either or. I'm using 1 and 2, right? That equals I omega B 1 and 2. Okay, so there's a relationship between the amplitudes of the electric field and amplitudes of the magnetic field. So, and both these magnitudes are perpendicular to N, but then B is also perpendicular to E because it's related to N cos E. So, so B is also perpendicular, but it also perpendicular is hard to draw in here. So it's you draw B in here. It has to be perpendicular. This is for one of them because one is propagated, like this term is propagated in the plus N direction. So this wave is propagated in the positive N direction. This term is propagated in the negative. Right. So you need to separate the two terms. But once you fix the sign of K or sign of this two solutions, then this relationship is given by 7.11. Right. Jackson basically using this script B represent the magnitude. Script B is given by the script B, the magnitude is given by, so we cancel the I. If we absorb the plus and minus sign in the case of whatever the K or the N direction, that so the script B is related to K over omega. We have a K over omega, and then N cos the magnitude of electric field. And this K over omega, we already worked that out. K over omega is this plus or minus square root of mu epsilon. If you absorb this already in K, that becomes cos. Okay, so that's 7.11. All right. So the idea is that the wave is propagating with magnet or with amplitude perpendicular to the propagation direction, and the two vector in E and B, they are also perpendicular to each other and satisfy the relationship like this. Okay, so that's straightforward. And we have a name for these kind of waves with the amplitude perpendicular to the propagation direction. This is called a transverse wave. Okay, but, I mean, that's a name. And, it satisfies all these relationships. All right, so so far so good. And sometimes the next equation, Jackson in actually using this notation of the, instead of calling the solution B, you can work out the solution for X also. X should be B over mu. So the permeability of the medium is mu. So in that case, it becomes divided by mu. You have this epsilon mu and cos B, and this comes in terminology. You have n cos B and divided by this z factor. And this z has the dimension of impedance. I don't know whether you can see that. It's not easy to see if you are not familiar. If you have a background of engineering, you can see that. But this is of the dimension of impedance. And when we in chapter 6, when we consider the energy conservation, we have a section that define the impedance, and that you can find the equation that somehow related to that. And you can see this has a dimension of impedance. Impedance has the dimension of resistance, but it has two terms. We have the complex. S in general can be a complex number. So but it has the same. So you use the same unit. So the unit would be just like the unit of resistance using ohms as a unit in SI. It's kind of strange to say that it's related with a bit impedance. But anyway, this is just terminology. And especially with, if you consider vacuum, so C would be, by this definition, C square root of mu. So you can also talk about the vacuum. That would be zero. And Jackson actually gave the value 376.7 ohms. That's called the impedance of vacuum. It's again very strange. The first physical meaning again is not easy. The physical meaning of electromagnetic wave are quite straightforward. It's just solution of the Maxwell equation, and work out the solution quite easily. But the strange thing is this dependency, and that has the physical meaning they related to impedance. Even for vacuum, there's impedance, and that's kind of strange because we usually assume that you have material before you have resistance or impedance, but then vacuum obviously has no material. It's just vacuum, but it still have an impedance. Well, that's the terminology, and just because Jackson used that quite often later on, so just remember this terminology and what the value of this. What the expression for this z sub 0. And one of the complications why you use that that often is that it changed from Jackson originally has all the chapters in the Gaussian unit, but then later on he decided to change the SI. Probably the pressure is just too great to push people to use SI. But he's just used that up to, I think, up to the relativistic fact chapter. I think it's chapter 11. So up to chapter 10 using SI. Afterwards, stuff from 11, he still keep Gaussian unit. So that kind of strange. strange arrangement. But if you work out the same relationship using Gaussian, and that would be much easier. Then you have not have all these things. In Gaussian unit, all the fields are the electric field, magnetic field, even H field and D field all have the same dimension. So you can forget about all this complication, all this mu epsilon, all that things. Right? I mean, you still have a mu and epsilon, but mu and epsilons they are relative, what we call the relative, like the relative dielectric constant, or the relative permeability. They have that, they become dimensionless. They're just related, just relative to the value relative to vacuum. So, and then all this field will be just have the same dimension. Well, but again, which one? This is the speed, but then go back to Gaussian. This is relative. This is not. It becomes, you can say, it's normalized. So vacuum will have epsilon equals to 1. Like mu is also equal to 1. Okay, it's just a relative 1, very basic relative 1, right? So we actually there's some reason why Gaussian is more physical, because later on we see that we divide the energy wider. But if for electromagnetic field, the energy actually is oscillating between electric field, magnetic field, or electric energy and magnetic energy. They are actually equal partition. They have the same amount of electric field and magnetic field when they oscillate. So, and so to treat them differently is kind of strange. And then later on when we talk about special relativity, they are actually the same. I mean, elements of the same tensor. So naturally, they should have the same dimension and the same similar meaning. But I mean, for SI, you add that all these artificial dimension and make all the field different dimension. All the 4 fields are different dimension. HB, I mean D, H, and B. All 4 of them has different dimension in SI. But in Gaussian, they are all of the same dimension. Well, that's the reality. But anyway, we are up to 7.11.